everyone, we're looking at p-series, which are super simple. Okay, they're of the form 1 over your variable to some power. Okay, and we call that a p-series where p is your power. And now we need p to be a positive constant in this case. So really it's a negative exponent, but when it's in the denominator, we need it to be a positive constant. Okay, now there's a specific p-series where p is 1, it's just 1 over n, which is called a harmonic series, which if you know anything about harmonics or music or the way waves work, this is where each of your harmonics will be located on a string. Okay, now we can use the integral test to prove the p-series test. So real quick, I'm just going to run through some of these integrals. So if I do the integral of 1 over n, well, the integral of 1 over n is natural log, and kind of if you can run through it in your head, if I end up plugging infinity into natural log, I get infinity. So that means that my integral will diverge. Okay, now if I take the integral of 1 over n squared, well, I'll end up getting negative 1 over n. Okay, and if I plug infinity into that, that'll tend towards 0. So this should still converge, and if you actually go through the work, you end up getting 1. All right, and same thing for here. Kind of when you think about it, the goal is you want this degree here to be a sufficient power so that when you take the integral, your result is still going to be a fraction. Okay, because if this variable ends up in the numerator in any way, keep in mind you're plugging an infinity into it. And if you plug infinity into the numerator, it's going to tend towards infinity and diverge. Okay, so you could probably guess what's going to happen, but 1 over n cubed is going to converge. Okay, the integral of that is 1/2. Right here, if I take the integral of 1 over the square root of n, I end up with 2n to the 1/2 power. Right, and again, that goes to the numerator. So if I plug infinity into that, that tends towards infinity. So that's going to diverge. Okay, 1 over the square root of n is going to diverge to infinity. Okay, now right here, this is really n to the 3/2 power. Okay, that power is still big enough so that it will remain in the denominator. So if you go through that integral, you end up getting 2. And last one, you can probably guess. If you go through that integral, you end up getting 1/4. Okay, so by the integral test, I can show that all of these converge and all of these diverge. So let's come up with an overarching theorem. Okay, so let's come up with a generalization. That's really easy to use. Right, so basically, if my exponent here is greater than 1, it's going to converge. Always. Right, if it's between 0 and 1, so if it's a fraction, if I have a square root, cube root, whatever, that's going to diverge. And if it's equal to 1, which is our harmonic series, it is going to diverge. Yeah, that is a special series. So essentially, we want our p to be greater than 1. Right? If the power right here is greater than 1, it will converge. If it's anything other than that, it'll diverge. And you might be wondering why I don't have negatives included here. Well, if I have 1 over x to the negative 1, that's just x. And so, that's a whole nother thing. All right, so let's work through some examples. Right here, I have 1 over n to the 1/3 power. That means that p is equal to 1/3, which automatically I can say is divergent. Okay, I don't really have to do any work. Here I can see that p is 5/4. 5/4 is greater than 1, so it's convergent. All right, and that's it. P-series are super simple. See you all later.